My name is David. I am a recent master in AI graduate here at the University of Amsterdam. I did my master thesis with Sebastian at the Indie Lab, and he invited me to keep working with the lab on this particular paper, which we got published recently at the TRL workshop. It's quite the mouthful, parameter-efficient automation of data wrangling tasks with prefix-tuning. We presented it at the table representation learning workshop at NeurIPS, one of the organizers here, which is great. Super cool day to spend an entire day with people who have been working on similar things. So what I'll be talking about today is, first, I'll introduce the concept of data wrangling tasks. You're probably familiar with this, but just to give you an idea of what we're working with, I'll kind of talk about how language models fit into these kind of tasks. I'll talk about the prefix tuning methodology, which is kind of the core concept that our research was built around. I'll talk about our contributions, how we set up our experiments, and then give you the takeaways of our research. So first of all, when I'm talking about data wrangling tasks in this context, these are three specific examples. First of all, there's entity matching. So let's suppose we have this database with tables on different domains, different representations, and we want to know, hey, these two rows from different tables, are they talking about the same real world entity? Yes or no? Error detection kind of takes this single row and it wants to predict if the data in that single row is consistent. So for example, if my country is Spain and my capital is Paris, it should say, hey, there's something wrong here, the system that we're working with. And lastly, there is data imputation. Let me clear up the screen for myself quickly, which essentially means that we have these missing values, and we want to infer them based on the context that they're in, right? So we have 10 data sets consisting of these three tasks, and this is where we started from. There we go. So surprising or not, a bit sad as well, is that currently large language models, specifically GPT-3, large language models are able to achieve state-of-the-art performance on these kind of tasks compared to task-specific architectures or methods. So kind of to take you through this, how this is done is you have your tabular data, and what these methods do is they format the tabular data as text through linearization. So you just have all your attributes and your values, you kind of put them after each other to create this long string, which is then a representation of your table. Then using these large language models, you can feed this piece of text into your language model. And then you kind of need to give it some examples as well. I have some reverb. Okay, good. So how these large language models work is you want to prompt them. So you want to give them a task instruction on what they need to perform. So you want to give them a few examples of the task that you're performing, and then ask it a question like, hey, are these two entities the same? And kind of the main takeaway here is that the performance of doing this prompting is really susceptible to little changes. So if you pick your examples, for example, if you pick them randomly, your performance drops significantly compared to when you manually engineer the most optimal samples. And also this textual prompt that I was just talking about, like this instruction, like, hey, are these two entities the same? Question mark. Adapting that a bit can also cause a significant change in performance. So there are quite a few quirks there, but if you manually engineer everything in the correct way, these language models are able to achieve good performance on these kind of tasks. So this is very parameter efficient because you don't no longer need task and domain specific architectures. You just have this one model that you can use. It achieves great performance, as I mentioned. However, you can't really automate it because, as I just told you, you would need a human in the loop to kind of modify these textual prompts and look at the training data, which then also raises privacy concerns. For obvious reasons. So awesome paper by these people at Stanford, but not perfect yet, if we'll ever get there. But the question that we asked is there an automatable and privacy-friendly alternative to this way of working with large language models. Maybe fine-tuning. So I'm not sure how much of you are familiar with the concept of fine-tuning. It's a pretty general example, but what it essentially means is that you have your neural network, your language model, and you kind of adapt your weights based on the task that you're performing. So you want to do entity matching, for example. You have a training set with a lot of examples, and you adapt your parameters. So you kind of learn a new parameterization, but you start from an existing language model. You don't train it from scratch, you fine-tune it starting from an existing one. So this is very similar to the system that I just described with prompting, in the case that you again need to format your tables as text, and you want to feed them through your network. But instead of using these examples in the beginning, you kind of optimize your parameters now. If any of you have questions based on your background, I'm not sure what makes sense or what doesn't, but please ask. I'm happy to go a bit into detail. But this often is done with smaller models. Like in terms of language models, we have these huge language models like GPT-3 and ChatGPT that we've been seeing recently, but we also have smaller ones, and fine-tuning is often done on smaller ones. So in terms of performance, fine-tuning and prompting, as we call it, are at around the same performance. But with fine-tuning, we can now automate this process. We no longer need a human in the loop to manually type these texts, but we can train and adapt the parameters in an automated fashion. However, this also means that for each new domain and each new task, we need a separate copy of the model's parameters. So for example, if you have this cloud environment with thousands of tables and you want to use your models in this context, it's no longer feasible because you need thousands of separate copies of your model. So for the people who didn't follow, this is kind of the main takeaway. We have fine-tuning versus prompting. Fine-tuning means I'm adapting my parameters. Prompting means I'm just creating this really interesting prompt, a textual prompt. Fine-tuning is automatable and more privacy-friendly, but not so scalable. Prompting is not easily automatable and less privacy-friendly, but very easily scalable because you only need a single model. In terms of performance, these are very close in the tasks that we just introduced. So both still have their shortcomings. And we asked, can we take the best of both worlds? Well, in natural language processing or natural language generation, specifically in summarization, there's already a technique called prefix-tuning. And that's kind of what I want to introduce to you today. And how this method works is it freezes all the parameters in your large language model. So in that sense, you don't learn anything, you don't update anything inside of your main model. But you also don't construct this textual prompt at the beginning because you learn a continuous embedding that represents this prompt. So this is called a prefix, soft prompt. You kind of replace this textual prompting mechanism by learning a numerical representation. So to kind of give you some intuition, using a discrete prompt with modern day language models, you would kind of do it like this at the top, are entity A and entity B the same? And then you would like list your entities as I just described. With prefix tuning, we kind of replace that question and we use a continuous representation that we learned through some training data. Is this intuitively sensible to people here? Cool, I see some nodding heads. I will assume that's a good sign. So if we then learn this continuous prefix compared to creating this discrete prompt, this means that it's really parameter efficient because you only require 0.4% of the parameters compared to fully fine-tuning, optimizing all your parameters required when fine-tuning, but it's still automatable and privacy-friendly because you do it through an automated training procedure and you don't need a human in the loop to manually construct these prompts. So it sounds like it's the best of both worlds. And to kind of give you an overview of how prefix tuning compares to fine tuning, we created this figure. So how you need to interpret this is the big rectangles are the language models. If something is red, it means that the parameters are updated. And the white rectangles here are kind of the activation values in the network. So when fine-tuning, you update all your parameters, and your activation functions are computed by those parameters that you update. However, when prefix tuning, you freeze all the parameters in your main network, and you add these activation functions, activation values at the beginning, which are generated by a really small neural network. So in terms of scale, you can already see this is way more efficient than this. You introduce a few extra activations at the beginning, but that's it. To give a bit of a formal definition, the activation values in your the activation values that you're using for fine-tuning are all generated by your large language model. However, when prefix tuning, your first few activations are not generated by your language model, but they're computed by this really small neural network at the beginning, which computes this prefix. And then your language model is conditioned on the activations that you computed in the beginning, resulting in an output that's hopefully works well for the task that we're performing. So what we did is we thought, okay, this sounds great, especially for data wrangling. If you want to scale this to large environments with a lot of data, then these language models are not great per se, but this sounds great. So let's try that. We compared it to fully fine-tuning a model on these tasks. Sadly enough, most large language models like ChatGPT, GPT-3 are currently behind a closed API, so we were not able to perform our experiments on those kind of models. But as I just said, fine-tuning T5 currently achieves similar performance to prompting GPT-3, so we thought we could make that comparison quite fairly. So how do we format our data? I already talked you through this quite quickly. You want to represent your tables as text. So that's how we do this for our three different tasks. We list the attribute and values, and then ask a question based on the task we're performing. We used the implementation of the T5 language model neural network by Hugging Face. They have great implementations of most modern architectures. These are what our data sets look like. We have 10 data sets for the 3 different tasks. If you want some details on this, you can find the paper easily. For now, I'll continue to the more interesting stuff. Again, we compare prefix tuning, the thing that we did, to 2 other methods. Fine-tuning T5, this is kind of the baseline that we want to get close to or beat, but we're much more efficient. And zero-shot prompting GPT-3. This is a bit of a edgy comparison, as it's not really fair because we were not able to perform our experiments with GPT-3. But just to get an idea of where we are in the space, we wanted to do this as well. So first of all, a results table comparing prefix tuning with zero-shot prompting GPT-3. This is our performance. This is the performance that zero-shot prompting GPT-3 gives. And as you can see, we clearly outperform GPT-3 when zero-shot prompting. It's a bit of an unfair comparison because we use a much smaller neural network, but we also use training data, whereas they don't. But it kind of gives you an idea that this method works really well compared to just prompting these modern language models. And then the more interesting comparison, I feel like, is against fully fine-tuning the same neural network language model compared to our fine-tuning method. And you should keep in mind again here that we only use 0.4% of the parameters this is our performance, this is 250 times more. And this is the relative performance. So we get really close to fully fine-tuning for 5 out of 10 tasks within 2.3%. And even for the other ones, we're not that far off. So we thought this was pretty impressive with the limited capabilities that we had. The main takeaways here are performance is within 2.3% for most cases, or 5 out of 10 cases. So that's great. We're much better than zero-shot prompting GPT-3. And we think, especially when applying these data wrangling tasks in large environments, this is something this is an approach to really consider, because you can't just throw large language models at them. But this is an option that it really gives some opportunities in real world scenarios. So we thought that was awesome. Into the future, we want to, of course, experiment with applying our method to more extensive language models. New ones are coming out every week. So kind of looking how that, checking how that looks might be super interesting. Currently, our prefix at the beginning, this continuous prefix, is generated through a very simple neural network. It's like 1 or 2 layers. I'm not exactly sure, but it's extremely simple. There's nothing special happening there. But of course, we're working with tabular data here. Like, there are relations. We have multiple tables. It would be a super interesting question to ask whether or not we can capture this structure, maybe in a way and embed it into this continuous prefix. And there are already some approaches being done on cross-domain knowledge or even cross-language knowledge using a specific type of prefix called control prefixes. If you're interested, look it up or ask me. But there's, I feel like, much more work to be done here. So that's kind of it. I hope that it made sense to you, that I gave you some ideas on how language models fit into the data management space, that efficiency is really important. And this is just one way of that direction. So that's cool. And thank you for listening.